Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 8 from the universe to the atom. We're looking deep inside the atom, and we are going to be covering the last stop point here, the role of particle accelerators and their operation, how it validates the standard model of matter. So, like we said, we're going to investigate the operation of different types of particle accelerators. And then by the end of this, hopefully you have an understanding of the role the accelerators have in validating or testing our standard model. For further reading, you can always go through this textbook reference. Let's just get ourselves started by recalling what the standard model of matter was. Remember, we could break the model into two parts. We could have our fermions, so the matter creating particles. And then we had our bosons, which are the force carriers, so the things that allow for interaction with the force fields. When it comes to, quickly looking at types of bosons, which of the following is not a type of boson? The answer would be a meson. A meson is an example of a hadron, so a combination of a quark and antiquark. B, why is the strong nuclear force necessary? When we first talked about the strong nuclear force, it was designed to overcome the electrostatic repulsion that experiences by protons inside a nucleus. So we said that protons were positively charged. If they were all clumped inside the nucleus, they would be repelling against each other, electrostatic repulsion. Does anyone remember which particle exerts the strong nuclear force? Well, you consider that. That would go down to the neutron. So the next question we have is baryons, such as protons and neutrons, consist of 3 quarks or 3 antiquarks. Using the table, which of the following represents the quark composition for a neutron and an anti-neutron, respectively? So if we have a look, a neutron, we already recall, is made up of 2 up quarks and 1 down quark. How do we know? Because 2 up quarks, So we know that a neutron is made up of 1 up quark and 2 down quarks. The reason we know that is because 1 up quark has a charge of 2 over 3, positive. We know that 1 down quark is made up of a negative 1/3. So if we have 2 of those, that adds up to 0. So in this case, for an anti-neutron, they would have the exact same configuration, because what we can see here is it has the exact same charge values for the particular quark. So that means we'd have the anti-up and 2 anti-downs. So the answer is C. If you actually look at the analysis of this question, it's equivalent to a band 3 or band 4 HFC standard wise. So just recall what each boson does. So the photon allows for the interaction with the electromagnetic field, so it binds charged particles together. Also, it provides the ability to interact with electrostatic force, magnetic force. It also allows for the electrons to generate the chemical properties inside different elements. The Z and W boson, they interact with the they interact with the weak nuclear force. This interaction allows for nuclear particles to change, so that could be radioactive decay as an example. And then we have gluons, which are strong nuclear force. This allows for quarks to bind together to form hadrons, so that could be mesons or baryons. And our most famous examples would be the neutron and the proton. If we compare the fundamental forces, so the 4 types, the strong force is the strongest, hence the name, though the range of the strong force is very small. The weak force is progressively weak, but not as weak as gravitational force. Gravitational force is actually the weakest of all 4 forces in our universe, but it has the biggest range. So as well with electromagnetic fields. Electromagnetic force is the second strongest of the 4, and also similar to the gravitational force, it has an infinite range. Okay, so that's what we talk about there. We also know that the strong nuclear force is only attractive at an extremely short distance, or at really short distances. So it actually goes from repulsive, then attractive, and then it just weakens at a very large distance. But it is still the strongest force in comparison to the other 3. The gravitational force is the weakest out of the 4. Now, how do we generate mass in all the different particles? We already said last lesson that it's due to the Higgs boson. So we talked about how the Higgs boson, anything that interacts with the Higgs field, all those particles will clump together, and that's actually the way in which these particles would be able to gain mass. The photons do not interact with the field, and that's why they don't have a mass. That's what we talked about last time. Okay, so what we're going to be looking at now is the operation of particle accelerators. Firstly, let's look at the operation and how these particle accelerators work. So the purpose of a particle accelerator is to make particles accelerate near this or close to the speed of light due to magnetic fields, electric fields, and cause them to collide. Through this collision, we can look at the properties of the strong nuclear force, create new radioisotopes that might not exist in nature, and we can find new elementary particles from scattered nuclons. There are 3 types of accelerators. There is the cyclotron, the linear accelerator, and the synchrotron. Okay, so types of particle accelerators. We have the 3 that we mentioned here. Okay, so in terms of a linear accelerator, you can see the structure here. It uses alternating current to create changing magnetic fields. If you have a look at the structure of the tube here, so what we have is the evacuating tubes. The polarity switches to different directions as the particle is going from one tube to another. This is to allow the particle to retain the same direction of motion, but it's also to allow it to increase its overall acceleration. So we know that it's a long evacuated tube where the charged particle is propelled. So instead of saying an atom, it's probably more correct to say the charged particle. We are using AC electricity. The charged particle is accelerated by the electric field. This increases the overall kinetic energy. By reversing the polarity of the voltage, we allow for the particle to accelerate in the same direction and gain more speed. In terms of the benefits, one, it's relatively the cheapest to build and it's easy to use. Some constraints with it is the length of the accelerator. Because it is in one straight line, there is a limitation of how long it can be built, which means that there is a constraint in terms of the acceleration on the particle, or the acceleration of the particle can go, and so we might not be able to generate a particle that goes very fast as a final. And as you recall from special relativity, the faster the particle becomes, the more difficult it is to make it go faster. Next we have is the synchrotron. So you can see it's the reason why it's called a synchrotron, or cyclotron, sorry, is because it's causing the charged particle to move in a circular motion. So that's what a cyclotron does. In terms of the actual application, as you can see, there's a little gap in between the cyclotron. Now the design of that is once you inject a charged particle into the center, you have a static magnetic field and you have a high frequency alternating current, alternating electricity, causing the particle to spiral in a particular direction. This spiraling motion, okay, will cause the particle to increase its velocity. With the magnetic field, that's also going to cause it to go in a circular motion. So it's going to go in a circular motion and spiral out as the velocity increases. Once it reaches a desirable velocity, the particle is released for collision. In terms of the benefits of this design, it's relatively small, so it's more compact. In general, a lot of medical industries use a cyclotron because it's so small and compact. It's great at generating radioisotopes upon mass. The disadvantages of using a cyclotron is the limitation of the acceleration of the particles because of some variations in mass and velocity. So we can use protons in the acceleration, but we don't use electrons. The reason being is because the electrons have a really small mass, and because it has a really small mass, what we know from the centripetal force, if you recall, because the mass is very small, if I make the object go a little bit faster, overall it actually spirals out a lot quicker. So just a tiny increase in energy will cause the electron to spiral out of the cyclotron, and so we can't really get a nice build-up of energy there. The other issue is uncharged particles will not be accelerated in a cyclotron. The next one we have is the synchrotron. This is the main design of the biggest particle accelerators in the planet, or on the planet. And the design is very straightforward. So if we have a look at this diagram, again we have an electron gun that ejects our charged particle through into these tubes here. So that's our ejection point here, that's number one. And the particle will have a fixed amount of energy. Once it gets into the tube, it's going to be exposed by high frequency alternating currents that causes it to accelerate in a particular direction. You have magnets on particular ends of the path, or on the circular path, to keep it rotating in a circular path. And what it also does is it increases the particle's overall energy. This, out of all the particle accelerators we have, this one is the one that makes it go closest to the speed of light. Once it's reached that particular point, then you can release it through the target tube there. Okay, so that's what we're talking about here. So we have the electron gun that ejects the charged particles in a circular motion. The magnets will help accelerate the particles and cause it to deflect in a circular manner. the magnetic field strength of a synchrotron increases with the particle's kinetic energy. Now, the importance of that is, like we said, through this synchronizing process, we can account for the increase or the relativistic effects of momentum as the particle reaches closer to the speed of light. As we said before, the closer we are to the speed of light, the more difficult it is to make it move faster. So the fact that our magnetic field will increase because of that change makes it a lot easier to reach that speed, or that really high speed that we're looking for. So what are the benefits of using a synchrotron? Firstly, we can accelerate particles at really, really high energy. Second, we can see really high energy collisions. So the point of high energy collisions allows for us to potentially see other elementary particles of inside a subatomic particle or inside an atom. Disadvantage of using cyclotrons: you can only accelerate one packet of charged particles at a time, so it's a small packet of particles, and there is a high proportion of energy that can be lost in terms of the radiation. Don't forget, because we are having rotating charged particles, they will emit electromagnetic radiation, and that will cause a loss in energy. So it emits EMR. Okay. What we want to talk about is the probability of collision. Now, we say we're causing these protons, lots of these protons colliding in one go. Well, here's an analogy for you. Imagine you have two arches separated by 10 kilometers. And what they have to do not only is to reach the target to each other, which in a synchrotron it will be completely fine because you'll have enough energy, but in that 10 kilometer difference, they must find an opportunity where the arrows collide. Now, this is an extremely low probability, as you could imagine with this analogy, and that's the case with the synchrotron. So as much as an incredible machine that a synchrotron is, it's actually not that easy for a collision to occur. You might only get a couple of collisions for every 1,000 opportunities of releasing the protons. So this actually gives you a nice little chart of the different types of speeds we can reach. So the Large Hadron Collider, the LHC, that can reach 99.9999991% of the speed of light. So the closest thing we have in terms of the speed of light there. Alright, so the next we go to is the role of particle accelerators. The idea is very simple. By smashing charged particles near the speed of light, or what we can actually look at is the really small components of the universe. We can look at potentially the release of bosons. So we could look at how the particular charged particle was connected with particular bosons. We could find other components that might be within that specific particle as well. So, in terms of the initial setup, we want to accelerate the subatomic particles near the speed of light at really high kinetic energy. Based on special relativity, we have to also take in the relativistic effects caused by mass and momentum increase. And this also applies when achieving really high kinetic energies as well. So under these conditions, we can also look at the applications of special relativity. So that's quite interesting as well. When we do get high energy particle collisions, the energy of the collision can cause a transformation into matter, or it could be transformation into energy, but we could get a formation of new particles. Now, if we do get the formation of new particles, obviously they're going to be heavier, and most likely they are going to be unstable. So we can form new particles using the particle accelerators. But the value of having unstable or heavy particles is they will break down into lighter particles, which can also decay further. But the beauty of that is we can actually observe a successive decay chain, and we can look at different types of particles or radiation that is emitted in that process with different detectors. So what we want to do is, during that decay chain, we want to analyze any particular mass or particular energy that is released from the lighter particles. That can tell us a bit about the structure of the particle and its mass, and it could also tell us about the type of interaction it has with different fields. When it comes to the detection, there are 4 chambers in the particle accelerators that can be used. The most inner layer is called the tracking chamber. Okay, so that's just to observe everything there. We have the electromagnetic calorimeter, so that's there to detect things like charged leptons, photons. We have the Hadron Collider, so that detects things like protons and mesons and baryons. And then we have the muons, which are for the really large leptons there. So that's kind of how the detection kind of goes. The last one I really want to talk about is the Large Hadron Collider. Now, the Large Hadron Collider's main function is to fire really energetic protons in opposite directions and watch them collide to each other. This actual structure is completely underground, I think around 18 kilometers in length. So it's a really, really big structure. Now, in terms of its main role, or let's look at an achievement that it's provided. So it's actually demonstrated one component of the Standard Model, and that's in 2013 when the Large Hadron Collider observed a particle with a mass region of 125 gigaelectron volts. Now, this value was consistent to the predictions made of the Higgs boson when the Standard Model was first predicted and formulated. So this actually helped us discover, or the Large Hadron Collider was able to help us discover the existence of the Higgs boson. And that's really important because the Higgs boson demonstrates how mass is gathered by particles. If we didn't find the existence of the Higgs boson, we couldn't really demonstrate the validity of the Standard Model there. We can also have really high energy collisions between protons, and that can help us see the top quark. So that's another way we can show it. High energy proton or positron and electron collisions can also release gluons and the W and Z bosons there. Alright, so that concludes the lesson, and that actually concludes the entire syllabus. So we've actually come a long way from Module 5, or actually starting Module 1 really, to all the way to we are in Module 8. So that covers everything you need to know of Module 8 of Inquiry 5. I do hope you've enjoyed this journey with me going through all these different concepts. I wish you well, and keep staying curious and enjoy.